It's the idea that like an aggregate of, call it experts that have an idea, is going to be better at correcting mistakes so that the aggregate is better than the sum of its parts. Ironically, usually the way of aggregating is a sum of some kind, so it's either a vote or an average. So it becomes a little bit ironic. So let's start with, like, there's a lot of methods. One of the easiest ones is bagging. So bagging is short for bootstrap aggregating, where you differentiate the models with the data you train them on. So you subsample your dataset, or you resample your dataset. There are some different recipes. And you train new models on the samples. Which means that all your models are going to be similar and are going to have similar performance, probably slightly worse than if you trained the model on the entire thing, on the entire data set. And you can actually, in some versions, you do include the model trained on the entire set as well, because it's just one specific case of sampling. But then when you aggregate them, there's some work that shows that you get a better vote. So usually, yeah, M equals Z, which means that you pick M elements from a data set of size Z, and usually if you have, like, say that we're talking about Cypher 10, you take 50,000 and you sample 50,000. It's just that there's going to be some repetition in the sample. I'm not a big fan of math, so I'm going to skip it. Also, it's not great for conversation. Happy to go over the details if you're interested afterwards. For boosting, so AdaBoost is one type of boosting algorithm. We take a slightly different principle, where we train a model, and then we look at the mistakes that it makes. So the mistakes that it makes on the training set are the samples, the examples that get classified wrong after training. And then we overweight those in the next round. So now you have, how do you overweight them is one of the things that goes in all the different variants of AdaBoost. So the calculation of those weights is one of the things that changes. And how do you apply them into the model? So there are some models that support weighting to the inputs, to the input examples, and some models that don't. So if you don't support weighting, you use the weighting for a random sample. So you change the probabilities of sample. And so you get that effect by proxy. Let's see. There's lots of different versions, Multiclass. The generic hand-wavy meta way of doing it, which most boosting algorithms follow, is you start with a uniform probability for all the samples, or a uniform weight. And then you define a stopping condition, which is usually you arbitrarily decide a number of rounds. Then you pick from your set based on your weights, create a new classifier, get your errors, identify the coefficient that you're going to use when you aggregate. So the aggregation becomes a weighted average of the outputs. And then you calculate the next distribution based on the errors that the algorithm makes. So actually the interesting thing is that the original paper for boosting provides proof that weak learnability implies learnability. It's a very interesting read. It's a bit heavy. It's fun, if you are so inclined. There's a bit of math. But it gives proof that if you can learn better than random, you can learn arbitrarily. Now, there are some caveats to that usually, and one of them is the size of your data set. But it means that the problem is learnable, right? And so that then actually has a lot of different branches going off of it. So one of them is ensemble theory, so that is the one that I'm interested in. One is information theory. And ensembles and information theory actually tend to overlap in some places. And the third one is cryptography, because it means that if you can learn something, it's not random. And so there are a lot of papers in cryptography that cite ensembles and boosting in particular, which is a bit of it, like you have to stretch your brain to imagine it, especially if you start looking deep into the math. But I think like it's very interesting if you're like at 2 a.m. can't fall asleep. It's a great way of speeding that process up. Let's see. So yeah, this is distillation from M1 to M2. I don't really want to go into it because we don't have that much time. Okay, so then there's. So I'm gonna stop here for a second and mention something that is kind of in the abstract and in the introduction, which is these two methods, bagging and boosting, and lots of other methods, except for random forests, have this peculiarity. So in ensemble theory, you will always see a learner represented as HT, of like some symbol that represents your inputs and your parameters. What this means is that the ensemble methods don't care what learning algorithm you're using. Which means that you can do bagging on trees, you can do bagging on XGBoost, you can do bagging on, I'm going to rewrite this, you can do bagging on deep networks, you can do, I don't know if anybody's actually done a lot of work on bagging with LSTMs, but in theory you could. So this is good because it means that the method is generic, but it's also kind of weak because it feels like you're leaving a lot of insight on the table, right? You get a generic method, you can apply it to any learner that you want. Surely there's a way of doing things better that if you make some assumptions about your learner, right? Case in point, random forests. So random forests work by subsampling vertically, so bagging subsamples your data set horizontally by example, random forest subsampled by feature set, but they make some assumption, and the assumption is that your learner is a tree. That's why it's actually called random forests. So there are two methods that I wrote based on that principle, and they're very similar methods. And they came one straight after the other. But the assumption here is that you can do transfer learning on your models, and that you can increment the size of the model after training. I don't know why I'm writing this down. I can actually stop. So there's a lot of models that fit this. Usually in ML, when you're giving an example, running an experiment for some theoretical method, you use data sets that exist in the wild that everybody knows, which usually ends up meaning convolutional networks and CIFAR 10, CIFAR 100, ImageNet, all of those. Now,